In addition to my normal daily work as a sensor developer, I'm also one of 88,000 volunteers at the THW. That's the German Federal Agency for Technical Relief. Internally, we call ourselves helpers and are organized into 668 local sections. Each local section houses at least one technical platoon that consists of approximately 30 helpers. The technical platoon is made up of a command squad, a rescue squad, and a technical squad, while the technical squad specializes in one of over 12 different areas, such as electricity, infrastructure, water hazards, and more. I am a helper in the command squad. Our primary role is to support the platoon leader by managing radio communication and creating a situation map. When deployed to disaster areas, mobile phone networks and the internet are often unavailable due to power outages. In such cases, we'll rely on this radio device, which resembles a mobile phone from the last century. But spoken communication can be challenging, especially in noisy environments. At the THW, we are also trained to extract coordinates from paper maps using the UTM-REF coordinate system. A recent time-consuming exercise involving paper maps inspired me to explore a digital alternative to simplify this process. This is particularly important when we are deployed to disaster areas beyond our home regions, where we often lack access to local maps. Let us state the requirements for the digital situation map I developed here. It should function without internet access and the electricity grid. The map should be accessible via Wi-Fi. It should provide full coverage of Germany. We would like the ability to draw directly on the map. A search for places and streets based on the address would be desirable. Additionally, at the THW, we are accustomed to using the UTM-REF coordinate system. I present that in a live demo running from this device. And it will be followed by a short discussion how to enhance that map by data updates via a LORAWAN network. And now I'm going through the solutions that I developed along the path. To host the map, I selected a Raspberry Pi 02W. It is low cost, energy efficient, and can easily be powered by mobile power sources. To create a Wi-Fi access point with the Raspberry Pi, I used a script from Raspberry Pi connect.com rather than reinventing the wheel. If no known Wi-Fi network is found, it creates a hotspot. When a known network is detected, it connects to it. This simplifies system updates at the home base. Now my talk uses OpenStreetMap, and to bring you up to speed, the fundamental element is a node, which is defined by its location, meaning latitude and longitude. The next element is a way, it's a collection of nodes. And finally, there are relations which consists of nodes and ways. Each of these elements may have several properties to describe them. OpenStreetMap is distributed in the protocol buffer binary format, PBF, where the data for Germany is approximately 4.2 gigabytes in size. The large OpenStreetMap file cannot be served directly to users. Instead, I used plaintiler to create an MB-tiles file. MB-tiles is based on SQLite and contains tiles of the relevant data for various zoom levels and locations. These individual entries in this database are served via a FastAPI instance running on the Raspberry Pi, where the endpoint looks like shown here. To display the map, I used leaflet.js for map rendering. Then there is a style file determining how and whether features from the OSM file are displayed. For the offline version, I had to modify it a bit. So I took styles from OpenMapTiles, but modified the local path, which modified it to use local path for the tiles, the fonts, and the sprites. The sprites are the icons you can see here. For an efficient location search, I downloaded a GeoJSON file describing the postcode regions. I selected a medium precision for the shapes to conserve memory and processing time. I conducted some checks in my hometown to ensure the selected precision did not significantly affect the results. So meaning that the houses which are in one postcode region remain in that region even after simplification, and that the border is not moving too much. However, searching within these GeoJSON shapes remains computationally demanding. To address this, I created a Python module in Rust using Py03 to accelerate the search. For me, the main challenge was that most Py03 tutorials did not include examples where a class is initialized once and accessed multiple times via instance methods. You could find my implementation on my GitHub page. Here's the Python path using that module. Here we first read the GeoJSON containing the postcode areas. We can then either query the postcode for given coordinates or retrieve the shapes matching a specific postcode fragment. Now let us return to the OpenStreetMap PBF data to extract places. I used PyOsmium to extract all nodes which have a name tag and a place tag of the types specified here, so that I can get more or less everything from a large city to a small village. Then I stored this information in an SQLite database for further processing. In case of the streets, I did it in a similar way. Here I was extracting ways and not nodes. The ways include nodes. Again, a name tag must exist. A street without a name doesn't make any sense for a search. And here the important tag is the highway tag, where there are several, many different types. I did not list all them here. I think it might about 10 different that were relevant, from footpath to huge highways. And again, I stored them in an SQLite database. In the next step, the extracted places and streets are matched to postcode regions you have seen earlier. And this clustering is important because the names are not all unique. For example, there are 79 places named Altstadt, meaning historic city center in Germany. Similarly, Hauptstraße, meaning main street, is the most common street name with over 6,000 occurrences. To reduce the size of the data, I simplified the streets to a single point per cluster. For this procedure, I used the Shapely library. In this example, you can see the Emsauenallee consisting of two ways. First, I created a centroid of the green segment here, looked for the point on the street, the node on the street, which is closest to that centroid, and then took this as simplified point for this part of the street. Second, I repeated the same procedure for the red segment, and then finally I selected from both segment the point which is closest. And that provided me a single point describing that street. Yeah, next, as I mentioned, we need a coordinate transformation. So when you may be familiar with the latitude-longitude coordinates for locations on the globe. However, there's the so-called military grid reference system, MGRS, which is in Germany called UTM-REF. There the world is projected onto 100 kilometer squares with a two-letter code. And each of these squares describes a 200 kilometer square. And the precision of the location within this square increases with the number of digits provided. For practical purposes, a 10 or 100 meter precision is usually sufficient. The conversion between latitude, longitude, and the UTM-RF can be performed using PyGeodesy. However, there is some zero padding required as it expects at input float values in meters. So although this here in the 10 kilometer resolution is a valid UTM-REF coordinate, PyGeodesy would provide an incorrect result. So it needs to be converted into meters by zero padding. After all that theory, I will show a live demo hosted on this Raspberry Pi, where also the talk is running from. It's based on a typical scenario in my hometown. This year, about 10 World War II bombs have been found in the construction area close to the central station. Before the state's specialists defuse the bomb or detonate it in a controlled manner, more than 100 volunteers are alerted to clear the whole area around it. This means that people are demanded to leave their homes until the area is safe again. Now let's try the demo. This demo is not representative in all detail, and I simulate a typical workflow by the messages that appear in the upper left if I click on that radio device symbol. Here it starts with, we should provide the coordinates for the assembly point in the Stadtwerke parking lot at Luisenstraße 49074 Osnabrück. So let's try to start the postcode, and from the Raspberry Pi it may take a short moment to react. It's a bit slower than expected. Oh, thanks. I just mistyped the field. Yeah, so if I start with two digits, I get a really large area. Then I do it more precise, and then I get that certain region. Now I'm looking for the street. In the background, there is now a query to the SQLite database looking for the street in that postcode region. And now, but I don't know where the Stadtwerke parking lot is here, but I switch the style to another one. And here I see there are also always, or here many parking lot symbols. And here's the one from the Stadtwerke. Now I click here. I have my location picker. And this provides me with the coordinates and also gives information on the administrative area where this is. And here on the bottom, we have the coordinates that we could supply to our fellow helpers. So let's continue. There's an evacuation required in a radius of 1 kilometer around this coordinate. Then we would enter it here. Okay, here the location picker might be useful again. Then I'm putting a marker here. As it is a bomb, I mark it as red. Looks more dangerous. And okay, now if I move my cursor over it, we have the information, there's the bomb. Now I switch the color again. And as we should evacuate in a 1 kilometer radius, we can just draw a circle. And we don't need to be filled. And our mission is to handle the operational area A southwest of the railway tracks. You can see here the railway. Maybe we switch the layout back to that one with less symbols. Now let's draw our operational area, and the operational area should be called A. Okay, now the Detmarstraße is cleared. I don't know where it is. Maybe I should just look it up. Here it is. And as it is cleared, we take the green color and draw a line. Now we get a message, a person at Kollegienwahl 11 refuses the evacuation, the police is required. So here is directly that house number, we put an icon here and label it with, and then we get the message, Schlagforder Straße is cleared, then we just continue with drawing green lines here. And finally, the police arrived at Kollegienwahl 11 and removed the person, so we could remove the marker again. So this is a typical workflow. But for the whole mission, it would be helpful to have a live view of all the units' positions. So let me now switch gears and let me present the infrastructure that I'm currently developing to develop this in my situation map. This is why I'm considering integrating LORAWAN into this system. LORAWAN operates at 868 megahertz in Europe. It is designed for long-range, low-power and low data rate applications. All messages are encrypted. Its low energy consumption means that the battery of a sensor node measuring temperature or water level may last for several years. However, a GPS tracker may only last for a few days depending on the update rate. Typically, the infrastructure consists of gateways that receive sensor node messages and forward them to the network server. Here, I'm using the ThingStack sandbox, which is connected to many gateways all over Europe. The gateway cannot see the message content as it's encrypted, and it's finally decrypted and decoded on the network server. An alternative would be to run a local network server like ChirpStack directly on the device. Now let us take a look at my range experiments. I started with a gateway connected to the Things network stack sandbox and a temperature sensor node. The gateway is located on my balcony about 5 meters above ground. I took a short walk to check where data transmission was possible, which is labeled green, and where it was not, which is labeled red. The range limitations began approximately here at 400 meters in a residential area, but extended beyond 2,000 meters in areas with mostly free line of sight. But as I mentioned, I'm developing this for disaster applications, which means that we cannot rely on the cloud in the internet. At first, I was considering just to make my own cloud on my local device, but then I decided it would be more useful than in that cases where the internet is still available to use that grained coverage, which covers more or less Europe from the Things network, but have a fallback for the local application. And this is done in my case, which is currently under development. Yeah, but you can see the progress in my GitHub repo mentioned there. And here I'm extracting the session keys required for decryption from the Things network cloud, store them locally in SQLite on my device, and have the option to decode them directly there and provide, in case of an internet outage, at least for the devices where I know these keys. As for all my own devices, I should usually be able to extract the keys from the cloud. And then I have this as a fallback solution and have a limited range compared to Europe. It turns down to just about, let's say 400 meters to a few kilometers, but I could still receive data then. And with that, I would like to conclude. Thank you for your attention. If you have any questions, feel free to ask.
Okay, so we have about 5 minutes, 4 minutes. So if you are on this side, otherwise raise your hands. I can bring you the microphone. Yes.
Hello. My question is first, is the development related to spreading help on a disaster area, or is it also helping locating disasters? And secondly, can you name some limitations, hardware and software-wise, specific to the tool and the objective of the application?
Yeah, so currently is more or less just to help for navigation and drawing a situation map, like labeling things. As in the THW, we are more working technically. I had an example in that way, so I don't know what you mean by directly by health applications. So it may be if there is some information where people have been picked up by ambulance or required assistance, things like that could maybe put also in that map. And yeah, the limitations are more or less on the hardware with the Raspberry Pi. So when it's about the map, Europe, including shapes for more or less every single house, could still be handled. However, when it's about the street and postcode database, you have seen it takes a few seconds. Maybe there's room for improvement. And it also relies on how good that information is available in OpenStreetMap where to extract it. But in principle, that solution could be applied to at least the map, to every place where OpenStreetMap data is available. Yeah, if that answers the question.
Oh. Any more? Oh, good. Any more? Yeah. I will do some exercise.
Thank you for presentation. I was actually evacuated 1 week ago in Stuttgart, and I have a kind of a silly question. So like my safety was depending on the functionality of the Raspberry Pi. Thank you very much.
What was the question?
Yeah, do you have high availability for Raspberry Pi? So for example, I don't know if 5 helpers have the same device which can work in a cluster or something. So what if it rains or you drop your Raspberry Pi or something? Okay. And yeah.
Yeah, so in this case, the idea is more or less to keep the Raspberry Pi in the vehicle of the command squad, which is responsible for the 30 helpers in that case that are coordinated from there. And maybe it could be an option, as it is really cheap to put one, at least but for navigation issues itself, you could also use some TomTom or whatever. But in this case, it's about drawing on the map, what you could normally easily with paper maps. But yeah, it's just the combination that you can combine that. Yeah.
Yeah, so I have a question about the user interface. Do you only use it in the command vehicle, or do the ground teams also use that? How is it handled through touchscreen devices?
The idea is to use it in the command vehicle, but on many different devices that are available. So maybe a tablet, a laptop, or maybe a smartphone. Yeah, that's the main purpose so far. And often when we are deployed to some area, we may just know a few hours before where we go to, or may even not exactly where we go to. Then it could be nice to have data for the whole of Germany or the respective area. It saves some time for preparation otherwise.
First of all, thank you. This is a really cool project. I was wondering about the decision also to put it on a Raspberry Pi. If you're only using it in the command vehicle, where you already seem to have like a lot of devices available, wouldn't it be sometimes easier to just run it on one of those devices?
Yeah, it depends on. So some of the devices available to us, so officially we don't have any devices. That's not true, in fact, but there may be a tablet provided by the firefighters. There may be some computer bought from donations and so on. So there is not the official computer in the vehicle. And for the vehicle to have power available, we usually need an electricity generator outside, and that's not in the vehicle. It needs to be provided by another group, and that may not always available. For example, by our rescue squad, that could provide an electricity generator for us. Otherwise, we have to rely on the vehicle battery.
Okay, great discussion, great talk. So let's talk Jannis once again with a final applause, please.